Okay, continuing on, because we really need to get this through. Java versus C++ with arrays. So, all right, void arrays. So we have int x sub 100. Oh boy. And then we have int star y equals new int sub 100. Are these both arrays? Yes, they are both arrays. What is the difference between these two arrays? X is on the stack. Y,
not y, but what the y is pointing to.
Yeah, exactly. Perfect. What y is pointing to is on the heap. Y is on the stack, but it's storing memory location of something that's on the heap. All right. So now this is where it gets kind of confusing, because x actually, this is even more confusing. What is x actually? This is tricky because the syntax is weird.
Is it an identifier?
Right, oh, sure. It's an identifier. Is x a pointer or not?
Yes.
X is a pointer. It is pointing to something on the stack, which is the allocated integers. So both x and y are pointers. That's why this syntax can be very confusing. So 0, I is less than 100, I plus. That's why you can just do x sub I equals y sub I equals I plus 100. Because they're both being accessed the same way. And then I can just do printf x sub, let's say 10 equals %d x sub 10. All right, let's run that. Wow, it ran. Okay, great. Just to make things even more confusing. Oh yeah. What's Z? Let's make sure that compiles. Perfect. What's Z? A pointer that's storing the memory location of not x, but the array of integers that x is pointing to, which happens to be on the stack. Did everyone get that? Well, remember, I said a pointer can point to anything. So can a pointer point to a pointer? Yes. We haven't gotten there yet. It's not pointing to a pointer. It's actually copying the memory location of x into z. But yes.
How do you make it point to x itself?
How do you make it point to x itself? Oh, that's beautiful. S is a pointer to a pointer of integers, of an integer.
Can you make a pointer pointing to a pointer pointing to?
Yeah, you can keep doing that as much as you want. Actually, I think it's 256 is the number of how deep you can make your. But actually, that doesn't matter because you can always do what is it called? You can always conversion.
That's pointing to all those other things.
Right. Yes.
Is there a limit to that? Like, why would you ever want to do that?
What's a 2D array?
Oh.
Yep. You have an array. Each array is one row, and so you'd have multiple pointers, so you can jump to each row and then go to the correct column,
Okay.
or the other way around, whatever. Okay. Oh, this is gonna be fun. All right. So z sub where are we going? 10 equals 101. Actually, not 101. Let's make it 9001.
Whoa.
Whoa.
It's over 9,000.
Who's going to have 9001?
X,
Right, why x?
because z is pointing to the same location as x.
Uh-huh.
Cannot convert to,
None
oh,
of them will.
yes. This is why I was saying the syntax is very strange. Now we're okay. Please ignore that for now. I don't want to get into that. All right, x sub 10 is 9001. Perfect. Okay. Oh boy. All right, so we're going to dereference s sub 10 equals 9002. Let me make sure I did that correctly. Nope. If I dereference s, which is really the reference to x, and then I jump over another one, yeah, I did not like that. Can I do that? Oh, it wants the double dereference. This is where things get really, really weird. It's not going to take it. Oh well, I'll have to get back to you on that one. This syntax gets very, very strange, especially when you're operating with the stack. That's the problem. Yes? Oh, I thought you had a question. Because in reality, you want to be doing this. And then that should be just fine. And I think this syntax works just fine. Yeah, that syntax works just fine. So we'll dereference S, go over to value 10, and then it's happiness. Oh, of course it is. Perfect. Because the stack, stack operates very differently. All right, what am I doing? Because this was all very confusing, I bet, especially since I did it really fast.
Printing numbers.
All right, what is this line of code doing? First off, S is on the stack. What is the type of S? It is a pointer pointing to a pointer which points to an integer. Maybe. In this case, yes, because what does this line of code do over here? Generate the address of Y. Y is on the stack. So S is going to hold the memory location of Y. Y, of course, is on the stack. So when I'm down here and I dereference S, what is that really? Y. And then I'm going to jump over 10 spaces, or I'm going to add 10, sorry, to the memory location, dereference that, and that's going to write to the heap, which happens to be this array up here. All right, anyone not thoroughly confused?
Good question.
Yes.
I get the concept of it, but I feel like when I go to try and use it like a code, I'll probably get confused with kind of pointers.
Great. If I've taught you that, we're good today. Because yeah, you got to be very, very careful with pointers. When you have issues, what is the type? What is actually being stored there? Okay.
So, when exactly do you need the ampersand again? I think I was lost.
So the ampersand is whatever you want to take the memory address of something. For example, if I did, I don't know, sorry, YY, and I wanted S to alternate between Y and YY, I could just choose which one over here. There's different times for it.
Okay.
It's going to become it's going to make a lot more sense when we do function pointers, because then you're just going to take the memory location of the function and then pass that along.
Got it.
All right, we got to get going because we are out of time. Declaring arrays. All right, these are the different syntaxes. You'll get used to it. The big difference is in Java, the solid brackets are used in front of your arrays. In C++, please, please, please always put the star next to the variable name. If you don't, you are going to confuse yourself. For example, if I did this, int go star B, I'm sorry, int star B comma C. What is that doing? It creates one pointer. B is a pointer that points to an integer. C is just an integer. So don't ever put the star over here. Always put the star next to it, because now it makes exact sense what's going on. Okay? Okay? Just do it this way, guys. Yeah, trust me, just do it this way. And don't use the solid brackets, because that means something else. All right, we talked about heap, how you allocate it on store. That's great.
Did I forget my glasses at home?
Yeah, that thing got real fuzzy fast. All right, other languages do a garbage collection for you, like Java. Y'all are going to probably like Java after this course. All right, good. We talked about static, stack, and heap. What's stored in static? Global variables, your code. What's stored on the stack?
Dynamic memory,
Which
which is your variables.
variables associated with functions. So all your data with functions grows and shrinks on the stack. A heap is where your real dynamic memory is, or your heap allocation, objects or whenever you just need to grab a piece of memory. How long does something exist on the heap? Until you delete it. How long does something exist on the stack? Until the function returns. How long does something exist in static? The entire program. Everyone got that? Memory leaks, failure to free storage when pointers are reassigned. So yeah,
What's the worst that happens?
you run out of memory. Your program crashes. Yeah.
That's not the worst.
Well, I mean, if your program is keeping someone's heart alive, that might be bad. That could be bad.
That situation.
Yeah, that might be a little on the bad side. Just throwing that out
right
there.
here.
Yeah. You have a question?
I was just asking, when you say run out of memory, is that like in the context of like if you're like
You've filled up all the memory on your computer and it cannot allocate any more for you.
Okay. That's what I was thinking. But
Yeah, that's. Yeah, y'all, nowadays you really don't run into that problem because we have so much, and plus you can go to your hard drive, but if you go to a supercomputer, that can't happen. And if you ever have to deal with embedded machines, like I said, keeping someone's heart alive, that can happen as well.
okay. Like the chance of that happening, you want to like minimize stuff. Like
Yes.
We want to eliminate that.
Yeah, you-
If it's
yeah.
real life,
Yeah, you don't want to have this problem. All right, dangling pointer. So memory is when you free it. Dangling pointer is when it's freed, but the reference still exists and you try and access it afterwards. C++ allows you to do this. What am I talking about? Let me go back to the code. Remember up here, where after I deleted the object of where Charles was pointing to on the heap, I went ahead and accessed that memory location and stored something. Charles is a dangling pointer because it's pointing to something that's been deallocated. And you should not be doing this. C++, of course, allows it because you didn't segfault. So that's okay, but so it allowed it, which is bad. That's what a dangling pointer is. How do you fix this? Right after you delete, always do this. Ooh, I did it again. That way, if you try and reference it, what's going to happen? It's segfault. It's going to segfault immediately. So, yeah. All right, garbage. I think we've talked about all this. Y'all know about no pointers, right? Good. And I think we're, okay, real quick, just to make sure it's crystal clear, C and C++ leave it to you to do the garbage collection. Right. If unused block of storage isn't explicitly freed by the program, it becomes garbage. You'll get C++ garbage. There are garbage collectors out there. They're not standard. Don't use them for this class. Yeah. Java, Perl, Python, and many other scripting languages have garbage collection. And yeah, there's no need for a delete after a new. Okay. Why? Here's the question. Why, for those of you who haven't taken my class before, why does C++ make you do the garbage collection? C++ came out when garbage collectors existed, and we could easily just add it to the language by now. Why do we choose not to? So you have more power over it. That's correct. That's a good answer.
Use the newbies.
Confuse the noobs. All right.
Would it have to do with like you were saying, like large scale programs, like that? What you were saying, like programs don't have to run. I guess you said on a supercomputer. Or something?
Okay, on a supercomputer, right?
Just manage every little thing.
Okay, usually the garbage collector is going to kick in, like if you try and allocate something and there's no memory available, Java immediately goes to the garbage collector and says, hey, can you free anything? And that tries to free it and then try and return it. So there's this loop right here. So it's pretty good about making sure you have memory.
I know that too.
What is it, Alex?
It's so C++ is primarily used for writing operating systems, so they use it to maximize efficiency.
Yep. So C and++ are operating systems languages, especially C, which means that running a garbage collector can consume too much processing power. What if you're, again, keeping someone's heart alive, and all of a sudden the garbage collector decided to run, and while it was running, you could do nothing else until it was completed?
Okay.
Someone did.
Right. It could end poorly. Right. So C++ is trying to give you the power so that you can do exactly what you need to do from a low level. Okay. And it is, in general, if you code it correctly, you will have better performance in general as well. Okay. Any questions about all that? Because I'm just going to go straight to your lab. Nope. Okay.